Hello everyone and welcome back. So it's time for us to dive into a new subject, and that subject is delegates. So let's go ahead and do a little bit of whiteboarding here. So the first thing I'd like to do is fix my D. There we go. Is go over our objectives that we would like to get accomplished in this video. First of all, we must understand what is a delegate. Next, syntax. Next thing is going to be the 3 steps in using delegates. Very straightforward. I'll just write 3 steps. What we're going to be looking at will be the declaration, the instantiation, and then finally, to use it, invocation. From there, we're going to take a look at creating a very simple application that will use a very simple delegate. So I just put create simple app.
That'll almost be the hello world equivalent of this entire topic.
Absolutely. As a matter of fact, in this we'll be analyzing the 3 steps. So we'll point out these guys right here. So after we've seen a very simple delegate in operation, then what we're going to do is start getting into some of the more specifics. And for those of you that are completely new to the concept of delegates, what I'm about to begin writing won't make much sense. But I do want this on the whiteboard as an objective so that as we work our way down to it, it's going to become much more clear as to what's going on. And by the end of this video, you will understand what these things mean. So the next is going to be passing a delegate as a parameter.
Well, I mean, since delegates are so closely related to a further way of working with methods, and the onset of delegate can look simple enough once you get the 3 steps of creating and using them down. But since we are indeed working with methods, we will have to address some of the more intricacies that come along with them, because of course you can pass parameters to them.
Absolutely. Multicasting is another thing I'd like to touch on. Again, probably looks like a big fancy word to someone who is new to the concept of delegates. Next is going to be working with delegates that have parameters. So delegates with parameters. Next will be delegates with return values or return types.
So once again, since we're dealing so closely with methods here, this is another implication of methods, and that is the fact that they can return information. So as we use them with delegates, we'll have to address this as well.
I'll just put values, be it whatever. And then finally, we're going to have a very simple example inside of XNA using delegates in the form of callbacks.
Right, this will be more of a practical example because the preceding examples are just simple console apps that show the specific topic at hand. Once we get into an XNA, we'll make an app that actually utilizes a delegate to give callback functionality.
That's right. So let's go ahead and get started with our first objective, and that is what exactly is a delegate. So let me go ahead and throw kind of a divider line down here. So here's the what. A delegate is really nothing more than a type that encapsulates one or more methods. Okay, we've seen types. You know, if I make an integer, that integer variable is a type. If we were to create a class called actor and we instantiate it, I mean, actor is a type. A delegate is nothing more than a type. So I'm just going to go ahead and jot down a type. But here comes the big important thing. It is a type that encapsulates one or more methods.
And this really is the key to delegates. As a method by itself, you generally don't think of it as a type, because types, the ones that we have worked on up until this point, are generally things that hold data and can be passed. They're either objects or references to objects, and they can be passed around to different methods.
Exactly.
When you're working with a method itself, you may have actually brushed on this very lightly if you have ever tried to pass the return of a method and have forgotten the parentheses on the method call, and suddenly the compiler complains that you can't use a method group type as something to pass. And so that means internally it's actually looking at that method as a kind of type, but it's not one that you can use in a tangible sense. You can't sit there and pass a method. You pass things to methods.
Exactly.
What we're doing with delegates is we're actually we're now encountering a type. Basically, the delegate itself is technically a type that can encapsulate a method. So if you make this delegate, now you can pass the functionality of a method around like it is any other type.
And that is so important. Next, in dealing with what a delegate is, basically it consists of two different components. We've got the reference and the object itself. So I'll just put our reference and the actual object. So if I was to bring my mouse over here, give ourselves a lot more room. So we've got a variable, and we know this variable contains a reference that is pointing over here on the heap to the actual object that exists. So this is the instantiated delegate, our object. So I'll just put object up here. But what's great about this guy is he contains an invocation list. So that's what this guy is right here. And in the invocation list, we can add methods. Now these methods are pre-existing methods, so it's not like we are defining a method in here, though with anonymous methods we can do that, though I'm not going to get into that here because this is supposed to stay relatively simple as an introduction to delegates. But basically these different methods that I am writing out here are nothing more than the name of a method that exists in your application, okay? Now, by putting these methods in this list, here's how this works. If we were to invoke this delegate, as if it was just a regular method, every method that is in the invocation list will be called, okay? One after the other. So, let me think. Everybody's used to calling, if we had a method called add num, right? And we called add num, that's going to do all of the code that was defined inside of the method add num. Well, let's say that we had a delegate called myDel. We call it, when we call it, it looks as if we're just calling a regular method. But when we do call it, what's actually going to happen is every method that is being stored inside the invocation list of the object, of the delegate itself, will be called. Okay?
So really, a delegate is kind of a special object, because what we've just briefly looked at here is two things that you normally can't do. One, the idea of storing methods into it, basically references to actual methods, because as I was saying before, that's something you generally can't do. I mean, what type would you use if you wanted to store a method as a field? You generally don't store a method as a field. If you were sitting there in a class, you either have a field or you have a method, and that method then must have a body that allows you to add code. The delegate is a special kind of object where we can suddenly point to methods as though they're references, as though they're types. And we're also able to use that object directly as though it were a method.
Right. Okay, so what kind of methods can we store in the delegate itself? We can store both instance and static methods.
So you can get some interesting effects out of that if you think about it, because what you had just drawn in the previous diagram is the fact that a delegate is instantiated. As you're looking at your stack and then your actual heap has the object itself, that object is an instance, and now it can point back to a static method.
That's right, which is very cool. Now, what do delegates allow us? So what do they allow us? No, that was fail. Allow us, there we go, to They allow us to pass methods as parameters because we're just dealing with a type. We've seen where we can come up here if we wanted to, and let me grab a quick eraser. We can have add num and we can send x, where x is a type of, let's say, of type integer. So we're passing whatever's being stored in x, which is an integer, to add num. Well, this is extremely important. We can define methods that take in delegates as a parameter. So now we can just simply pass this guy right here over to a method, which is really cool because that means the method we're passing that over to doesn't need to know anything about the methods that are being passed to it in order for it to call.
What's really interesting about that is if you look at a method as representing functionality, it is now as though we can suddenly pass functionality to somewhere else. Because exactly like you just said, when you're passing the method as a type, when you pass x into a method, you don't pass x and set it to 5 at the same time. That's not the point. You just rely on x is whatever x is.
Right.
Pass whatever x is on. Mm-hmm. If we're suddenly able to pass a delegate, that means we're at that time of passing, we're not concerned with what the delegate does. We're just saying whatever it does, pass it into here so that someone else can use it.
Exactly. We can also multicast, which don't let what I'm going to say confuse you. We can call multiple methods at once, not at the same time, so it's not a parallel call of all of these different methods, but it will appear as if we have called a bunch of methods at one time. In this particular case, I've set up myDel. This is a call to a delegate that we have established, and you can see inside here we've got 1, 2, 3, 4, 5 different methods in its invocation list. So by calling myDel, each of the methods get called one after the other, but we have simply made one call right here, and that one call was responsible for calling 5 different methods.
And really what that comes down to, since the delegate can encapsulate really whatever it wants to, it's not limited to one method. You can use it as though it was limited to one method. You can use one delegate to encapsulate one method and happily use it. But keep in mind that the way that that method is stored internally in the delegate is actually stored in a list instead of just one single field. So because it has list-style functionality, there's nothing that's preventing it from going through the entire list as it is told to execute, or told to invoke.
All right. We can also use delegates to define callback methods. And callback methods can be used in many different ways, but here's a very simple look at a callback. I can hand functionality over to a particular object's method, and one of the parameters can be a delegate. So I can hand it the delegate so that when that method was done with its functionality, it could then call some other functionality to occur. It could call some other functionality to say, hey, I've just finished doing something, or something's just occurred, or whatever it may be. But the nice thing is the method that we are calling to begin with, that we're passing the delegate to, has no clue who he's going to give a shout out to next. We can simply pass it a delegate, and that delegate is going to contain who we will call next.
It allows you to code those objects in a more generic manner, because now suddenly a collision isn't something specific to something like maybe your monster class.
Right.
You can make your game class put the specific handling in for collisions of a whole bunch of different objects, where those objects themselves aren't really concerned with what happens. They're just concerned with detecting that. So you can make 5 different objects, send them out into your scene, but since you instantiated them yourself, as you instantiate them, you can also say, all right, well, if this happens in your lifetime, tell us about it.
Yeah.
And so if that thing happens, then we get the callback back in our own code, and then we're free to define the specifics as we choose.
And we're going to set something like that up here at the end of this video over in XNA. Finally, they allow us to define events. You're going to find that delegates really serve as the backbone for events in C#.
And with events, we're talking about the actual type that is used in events. Also, if you've used any Windows programming with forms and you've used event handlers, this is literally what we're talking about with events and event handlers.
So now let's go ahead and take a minute, now that we've looked at the what. Let's go ahead and look at the syntax. The syntax is very simple. Basically, we'll start out with optional access modifiers. such as public or internal. Then the keyword delegate. Then our return type, or void if there is no return type. The delegate name, our identifier. And then finally, any optional parameters. Now we know that we are creating delegates to hold, to encapsulate methods. So we generally have some sort of understanding or idea of what methods we're going to put into a delegate. Now we all know that methods have signatures. Basically they have certain parameters that they're going to take in, various types, and they have return types as well. When we define a delegate, our signatures must match. That's very important to understand. So if I was going to put a method into my delegate, so into my object here, I was going to store a method that, let's say, took in a string as a parameter, but my delegate was not defined as having a string as a parameter, you would have an error. You've got to make sure that your signatures match. And we'll take a look at that as we work our way through this.
And what all this comes down to is you beforehand declare how the delegate works, meaning its parameters and its return type. You declare that beforehand before you ever get into a case where you start putting them into the actual encapsulation, meaning you've already got to know what kind of methods go in it before you actually add some.
Exactly. All right, the next thing I want to do, let's go ahead and just jump on back up. We've taken a look at the what. We've taken a look at the syntax. Now it's time for us to get into the creating a simple app, and that's where we will look at the 3 steps. So I'm going to, since we're not going to jump over into Visual Studio yet, or Visual C#, let's go ahead and just create another layer real quick. And let's just scribble one out. So I'm starting a new program, all right? We're going to start out, before we get into our class program, this will just be a very simple console application. I'll start by creating a delegate. No return type. So delegate void. Let's call it my delegate. And let's say my delegate takes in no parameters. We're going to start off as simple as possible. So this right here is the declaration of our delegate.
One other thing I'll point out just really quick here. Once again, if you are familiar with Windows Forms programming and you've worked with events and have noticed that you always have sender and args passed to it, that's why. It's because the event handler that you're generally using within Visual Studio is going to be defined as requiring parameters. So what we're going to do when we go to declare ours is we're declaring a brand new delegate that takes in no parameters.
Right.
But if you're wondering why you always had those passed in automatically with events, well, that's because somewhere in the library of code that you're using, the event handler has been declared as having parameters.
So we're going to make a public static void, a method called delegated function. Delegated function has no parameters. And if you guys recall, that's my cheap way of doing a console write line. So we're just going to write out anything. Hello world. And that is going to be the, and my pseudocode, that's going to be the end of this method. So if we call this method from inside of main, we're just going to simply see hello world written out to the console. So let's go ahead and create another, I'm just going to make it a little bit shorter here, static void main, and then our parameters. Now, let's use this delegate. So the first thing I need to do is go ahead and create my variable of type my delegate. So just like how we create an integer variable x, we say int x. Here I would say my delegate. So I first start out with my type that I have defined, and then the name of my variable. I'll just do a lowercase my. I'll just do my del. That'll be easier. equals. So I'm going to go ahead and instantiate this guy. So equals a new, in the type, my delegate. Now, as soon as I do this open parentheses, this is where IntelliSense is going to come in and give us, in this particular case, what it's going to say is that it's looking for void, open, close, target. This is what you're going to see in the little IntelliSense drop-down that's going to pop up. What that is saying is that we are looking for a method to go in here that has void for the return type and no parameters. That's what they're telling you. So let's say that we had a return type of integer and it took in a string parameter. Okay, so what I'm talking about is this guy right here. So this is going to be the delegated function that we're about to store in the invocation list. So let's stipulate that it had an int return and took in a string. What you would actually see here would be int parentheses string close target.
And just to reiterate, the reason that we're going to see void and then empty open closing parenthesis, well, look at where those come from. If you go back to the declaration of the myDelegate delegate, what do we have? Well, we have a return type of void followed by blank parentheses.
Precisely.
So that's exactly where that information is coming from.
And since we know this is the guy that we're wanting to store in it, they have to match.
And look at that same pattern once again. Void return type blank parameters.
Exactly. Let me go ahead and erase this out. Just give myself plenty of room. Okay, so in this particular case right here, all I need to do is say delegated function. And terminator. So I've created a variable on the stack called myDel, and myDel contains a reference that is pointing over to an object of type myDelegate, and this object has an invocation list, and the invocation list contains one method. And that one method is delegated function. So pretend I wrote it all out there. Delegated fun. There you go. So now we have a reference being stored in this object to this guy right here, which is very nice. Okay, so now we've instantiated it. So I can go ahead and say, in this all down here, we have our instantiation taking place. So the last thing in the 3 steps involved in using a delegate is invocation. So now, how do we use this new guy? Ready? Boy, this is challenging. Here it comes. myDel, and let's just treat it like a method. Doing just this right here is going to call every method that is being stored in your object, in your invocation list. And since we only have one method being stored in the invocation list, only one method gets called. So basically, this guy gets called and hello world gets written out to the console. So I could have replaced this guy with delegated function, boom, boom, and it would have looked exactly the same, and it would have ran exactly the same. And that, hopefully, helps demonstrate why it's very difficult giving an introductory lesson to delegates, because you really need a more involved setup for you to appreciate the importance of being able to establish delegates.
Exactly. It's very hard to describe exactly why you would need them, because it looks like we have just gone around the world to do something we could have done with one call.
Exactly. But as you will see later on, there will be times where we're going to set up very generic methods, and those generic methods are going to take in parameters. The types that we're going to be sending in are going to be delegates, where we can have different functionality that we're going to then pump into these very generic methods that then new functionality can get called, and that's very powerful.
because we'll be able to write classes where we can wait on making the functionality on something until later when we're handling something that has happened. Quite literally, if you want to swap this back to English, that means we are delegating the functionality that something can do to someone else.
Exactly.
And that's where you can get into a scenario like callbacks where that someone else is something like maybe a main game class.
Mm-hmm. Okay, so I would say it's a very simple setup. What do you think?
Oh yeah, it's not anything more than our current programs aside from declaring the delegate.
There you go. So let's go ahead and jump back real quick. And now we have seen declaration, instantiation, and invocation. We've created a very simple app. Now let's start to see one of the beautiful things about delegates, how we can pass a delegate as a parameter. So what I want to do is go ahead and jump back over here. And we'll hide this out just because that just blew my mind. And let's add just a little bit more. I'm going to create a new method down here. And this guy, let's call him something like show me. And show me is going to take in a single parameter. So we're just making a regular method here. This guy's going to take in a type myDelegate. And I'll give it a name. So here we are creating yet again another variable, a variable that's going to be local to the scope of the show me method. But this guy just happens to be a delegate. So now, instead of this line right here, I'm going to replace it. So this line's going to get replaced with this. I'm simply going to call show me. But I'm going to pass show me my del.
Once again, noting the fact that with my del here, we're not specifying the parentheses, which means at that moment, the moment we're passing my del to show me, we're not yet invoking it.
That's right.
We are just passing it. Nothing has happened. It's just in show me's hands to do whatever it wants with it.
Exactly. So where we had, remember this little setup where we had, here's my del on the stack. He's pointing over onto the heap to our actual delegate object, right?
Mm-hmm.
So we'll just say that's our actual object. And inside that object, we had our invocation list that had one method. So now we've just passed this guy. So here we are with del, and we've passed that reference over. So we're still looking at this guy right here.
And that's also key to remember is the fact that, like with any other reference type, since it's the same reference, we now just have another reference pointing to the same object.
Thing. That's right. Here's the beauty. Now I can turn around and to call, or basically to call its methods and all, I just simply say del, open, close parentheses, and that's it. So this is the guy that's now pointing, as far as scope is concerned, inside of this method. He's the guy that's pointing to our actual delegate object that contains the invocation list. So now we just treat it like a regular method.
And now what's interesting here is that if you look at it this way, the show me method or show me method's functionality can be changed based on what you pass it.
Mm-hmm.
Not just the data you get in and out, but the actual functionality. Because what if you had made another delegated function that did something entirely different, like erase the files on a computer?
Yep.
If you pass that to show me doesn't necessarily mean it has to print anything. It's
That's
taking
right.
in a delegate, and that's it. So as long as that delegate requires no parameters, you could have show me perform any kind of functionality you wanted it to.
And that's bringing us back to the whole idea of show me is pretty generic in this case. What does show me do? Well, it depends. It depends on the functionality we send to it, which is very cool. Okay, so let's see. How do I want to handle this next part? What do we have next on our list of objectives? Okay, so that is how simple it is to pass a delegate as a parameter. Multicasting. Multicasting is quick and easy. Yeah, let me go ahead and jump us back over here. And bear with me for 1 second. I'm going to erase this guy out. I'm I'm not going to spend a lot of time on this. I just wanted to mention that it's something that we can do, and it's going to affect return types when we talk about that in a few minutes. So let's stipulate for just a second that I have created two of these guys. So there's one, and let's pretend right in here, just to save us the time of me writing all this out again, I've created another delegated function, and this guy I've named delegated function 2. Okay, so we have one method right here, and we have one method right here. I'm not going to draw out the whole thing. So now, in this particular case, I have come in there and I have created my variable, and I've turned around and instantiated a new myDelegate object, and I've put delegated function in its invocation list. So here we are, object exists, here's my del over here on the stack, pointing to the object on the heap, and we have delegated function just sitting there. Okay? Now I have delegated function 2. That's the guy that exists right here that I haven't drawn out. How do we add him as the next thing down here on the invocation list so that we have two methods being stored in this object? It's really very simple. We can come in here and we can say myDel plus equals, and then simply add in the next guy, which is delegated function 2. And terminator. No parentheses. That's something that kind of makes me smile when I see a beginner trying to follow along with examples or trying to come up with some creative ideas of their own as they're sitting there just trying examples on a console application they're putting together. People want to come in here and start putting parentheses after this. No. That's not what we're doing. We're not doing anything that deals with calling this guy. We're simply adding a reference to this guy into the invocation list. All this does is put delegated function 2 as the second method in that invocation list. So now when we turn around, let's say that it said hello world 2. Okay, so the first method, this guy right here, contains hello world. The second one that I have not drawn out but we're all visualizing says hello world 2. So now if I turn around and say, all right, well, let's just run myDel. Run it, call it, whatever you want to say. Out to the console, you're going to see hello world and hello world 2. This is a multicast. We have just called multiple methods. Not in parallel, just so that there's no confusion, meaning that they all weren't called at the exact same time, but we called. It looks as if we have just called them both.
It's almost like you've queued up a list of methods to be executed, and by invoking the delegate, you've now begun running your way step by step through that queue.
Exactly. All right, let's go ahead and clear some of this stuff up. That is multicasting. Let's see what we've got lined up for you guys next. Delegates with parameters. Ooh, this is where things start to get a little bit more fun. All right, let's go ahead and clean up just a little bit more since this is starting to look kind of rough. We'll get away from the whole idea of multicasting. Logan, do you do any multicasting in Spacefighter?
No, I do not believe Spacefighter uses multicasting.
Okay, excellent.
Everything has been kept simple. It uses delegates for a few places, but it's only for one specific thing. I'm really just looking to make things generic. I'm not worrying about things like lists of method instruction queues or anything of that nature.
Excellent. Okay, so let's say, now, first, where does a delegate begin? A delegate begins with knowing what methods you're going to store in the delegate object. So that means let's go ahead and turn our attention first to this guy. So with this guy, I'm going to redefine him just a little bit. I'm going to say that he takes in a string. And we'll say this string is called N. Yeah, I'm lacking creativity today. Everybody has to just bear with me. It's better than X. Okay, so N is short for incoming, by the way. Just don't want to type it all out or write it all out. So anyways, we're taking in a string parameter. Now, if we were to try to compile right now, we obviously have a problem because our delegate does not have a signature that matches the method that we want to store in it. We have to change our declaration of our new type, our new delegate type. So let's come up here and do that. This guy needs to take in a string. And I'll call it X, just because I said that a second ago.
And also just to point out that, like with method declaration itself, we're only really worried about the signature that results from this.
That's right.
I mean, we're looking at it as my delegate string. X is just a nicety for once we're inside of it.
IntelliSense, revisiting that whole idea right here when we get ready to actually store our very first method into the invocation list, IntelliSense in this case would give us a void, space, open paren, string, close paren, and then it would say the word target, meaning target method. So in this case, we need to make sure that whatever method we're putting in there has a void return type and takes in a single parameter that is of type string. Very convenient. So that's what's going on there. So let's go ahead and undo a couple of those. So now that we've got this set up, what changes on this line right here? It's like, oh, we've got a parameter now. Nothing. The line looks exactly the same because dealing with the parameter means we're dealing with calling or invoking the delegate or the methods. We're not invoking anything right here. We are instantiating a new object and storing the reference to that object into a variable of type myDelegate.
The one thing I would like to point out is on that line is actually the line on which you'll get an error if you had, say, changed the delegated function's method signature and not changed your delegate's declaration.
Exactly.
That's the line you're actually going to get the error on, because it's as soon as you try to throw a method into the delegate that doesn't have a matching signature, that's the actual place at which you'll get the error.
That's right. Okay, so let me go ahead and try to keep this as clean as I can today. And actually, while I'm in here, since we are no longer going to be doing any multicasting, we'll just rewrite all of this stuff out. All right, so now how do we go about using this new parameter? So when we call myDel, does it look different? Yes, but not by much. myDel, and I'm going to pass it a string. Hello, you. There, just because I'm tired of hello world. And now let's go ahead and stipulate that up here, our console write line is we're going to write out whatever is in N. So when I call myDel, I pass it the parameter that each of the methods that are stored inside are expecting, in this case, a single string. So then the myDelegate object is going to turn around and call this guy, and it's going to pass hello you into this parameter. So now when we do our console write line, we're going to write out hello you. Okay? Logan, anything you want to add to that? Well, there's something I want to add to it. We know that in the object, we can store in the invocation list multiple methods. Every single method must have the exact same signature and return type. You cannot mix and match types in there.
Exactly, and that's what I was talking about, where if you tried, it will actually kick it out just upon method signature not matching. So basically, the other way you can look at it is that if any methods have managed to get into that invocation list, that means that their method signature does indeed match. That has already been checked, so you don't have to worry about passing in a string. You'll know that myDel already has methods that match the proper method signature.
Exactly. All right, so I do believe if we were to jump back over here real quick, that is going to leave only two things left. Going pretty smooth. Delegates with return values, and then finally our example, setting up some callbacks over in XNA so that you guys can finally get into doing something a little bit more fun. And then after this video, we've got a couple of other videos that we're going to present utilizing delegates that get just a little bit more involved. Right now, the whole idea of this video is just to tell you about delegates. So let's go ahead and jump back over here and talk about delegates with return values. So now we're dealing with returns instead of just void. So let us say that I come up here and we're no longer going to have a void return type. It's going to return an int. So notice how I'm starting with the method that's going to be stored or encapsulated in a delegate object. So we've now updated that. What's the next thing I need to update? Next thing is going to be this guy right here, because otherwise we've got a mismatch in types again.
Exactly, because you'll run into a scenario where if you try to put this new updated method into the delegate with its current type being void, you will once again get an error the moment you try to subscribe to that or add it to the invocation list.
Exactly. So let me go ahead and clean this up just a little bit. So let's say we're going to console.writeLine out whatever is in n, which is our string parameter. And then I'm going to turn around and say we're going to return
maybe in.length to get the string length that was passed in.
So in.length. Very clever, because I was just going to say return 5. All right, so we're going to return the length of whatever string that we set in here. Now, really, this program right now, the way I have it written out, would work just fine, because I don't have to put the return value into something. But if I wanted to, and this is just to save me from, just pretend all this is indented, I could say int x equals my del, and then I pass it hello u. So hello u gets sent into the delegated function, this guy right here, and then we console write out hello u, and then we return the length of that string back, and that length is then stored in here. It's that simple. The key thing to remember, the only tricky thing about a delegate is remembering, one, to declare it, and then after you declare it, it's the instantiation. But if you remember those two things, after that, you treat your delegate, your variable that you've created, and we're just going to call it a delegate, you just treat it as the method itself. And the cool thing is, you just call the method, pass it parameters, receive information back from it, and the object takes care of calling the proper methods that have been stored on its invocation list. It's as straightforward as that. There is one thing that I would like to point out. We're not spending a great deal of time with multicasting. I think everybody's got the idea that we can store multiple methods in the invocation list, but I do want to draw this real quick just to point out. So here we are, invocation list. Let's say method 1, method 2, method 3, and we are using this particular signature and return type right there. So that means that all 3 of these methods are all going to return integer values. So here's a wonderful question. If that was the setup and I called my del is going to cause 3 different methods to execute. Him first, then him, and then him. Each of these guys will be expecting a string parameter coming in. That's been satisfied. And each of them is going to have a return value. So the question is, what gets stored there? Simple. The last method on the invocation list, the return from that guy, that is the value that ends up coming back out. So that value would be the one stored right here, not the first 2. So let's say you had 10 different methods in the list. 9 of those would have their return values simply discarded, ignored, nothing's ever done with them. The final method that's called from the list, that is the return value that makes it back. I'm not spending a lot more time than this, except I'm going to spend 1 second to show kind of a shortened way of instantiating your delegate. But outside of that, I really don't want to spend a lot of time making people think that delegates are a big confusing thing, because they're not. Delegates are just a way of creating an object that holds a list of methods that you've already defined. And those methods can be static methods, they can be instanced methods that belong to, instanced objects. And then when you call the delegate, which you call as if it was a method, everything in its list gets called. It's that easy. So the last thing I guess I wanted to show before we jump over into XNA, let's go ahead and erase. I'm just going to go ahead and pull all of this out. Another way that we could go about doing all of this right here would be as follows. So as a matter of fact, I had no idea I was drawing that crooked. So let me just pretend that instead of that line, that's so much better, we wrote it out like this. I could have said, first my type, my delegate, and created my variable. So my del, terminator. No different than if I would have said int x, right? And we're so used to being able to say int x, next line, x equals 15. Completely valid. I can do the exact same thing here. I can simply turn around and say my del equals, and then the function name or the method name that I want to put on the invocation list. So let me fix my equals. So delegate it function. Here's the important thing. Terminator. No opening and closing parentheses right there. We're not calling anybody.
But you will notice that there is a little bit of compiler magic going on here because we didn't have to use new my delegate.
That's right.
Because we assigned to a delegate, the action of new my delegate was simply implied by the compiler.
And the compiler knows we need to go ahead and instantiate the delegate object and go ahead and store this very first guy on the invocation
So
list.
really it acts just as a shorthand for exactly what you did on the previous line.
Exactly.
You could probably even go so far as to declare and set up on one line. If you said delegate my del equals delegated function,
Yep.
you could do that as well, and then you would have exactly what the first line was, just minus the explicit instantiation of my delegate.
Exactly. One thing that I can point out when working with a multicast delegate, be real careful, because let's say I wanted to put delegated function 1 and delegated function 2. You might think that you could just start out and do this line, and then on this next one do plus equals, and then my delegate plus equals delegated function 2. You can't do that. This line right here is going to end up giving you an error because the compiler, as Logan just said, there's a little bit of black magic taking place behind the scenes. At this point, we have not instantiated the actual object. We have just created a container, a variable that's going to hold a reference to an object when you do instantiate the object. So if you try to do this guy right here, this first plus equals simply won't work. It's going to give you an error. You have to do equals for the first guy, and then this guy is now stored in an object that exists. Then you can turn around and simply do the plus equals to add. And while I'm on the topic of plus equals, we can also do minus equals if for some reason you need to take a method back out of a list. But again, that's kind of outside of the scope of what we're doing in the XNA 101 class. We just wanted to make sure that you had an understanding of what a multicast delegate is. It's just basically more than one delegate or method that's being stored in the invocation list. Plus equals to add additional ones. Minus equals will take one out. So if I said minus equals and then delegate function 2, it would take that guy back out. Okay? And the interesting thing is, not to really get too far off track, is these guys are non-mutatable. You can't truly just add to it or take away from it. Again, compiler's doing a little bit of magic behind the scenes. It's creating a brand new delegate with a brand new delegate list. So anytime you say plus equals, even though as far as you're concerned it still looks like the same delegate object, that delegate object has been destroyed. A new one's been created with the list properly updated. So that goes for adding or removing. Okay? Outside of that, Logan, is there anything else that you want to add before we jump over into
There's
XNA?
nothing really specific that's coming to mind.
Okay.
Again, just to sum it up, the whole idea is being able to encapsulate a method.
Yep, it's that simple, as I continue to say over and over. So now that we have taken a look at delegates with return values, we'll go ahead and jump over into C#, and inside of C#, we will put together our XNA example using callback delegates. All right, before we get started, let's go ahead and tell them what exactly is it that they're going to be putting together.
Well, in this example, what we're going to be doing is we'll make a simple XNA game, and in that game we'll have a circle graphic that bounces around the screen.
Okay.
That's what we're going to begin with. So we're going to make an actor class, and its job is just to move and to bounce off of the edges of the screen.
Okay.
Once we have that in place, we're going to put in functionality to allow a callback system so that our main game can be notified via callbacks whenever the actor bounces off an edge of the screen.
Okay.
That way we can have special and extended functionality that is put in place after the actor class is written and without modifying the actor class.
Okay.
So, to begin, I guess we can go ahead and just jump into things. I would like to point out that a graphic is going to be used for this example. I have it down in my working folder, which we could load very briefly. I would load it up in preview mode, but all this graphic is a white circle on a transparent background, which in the image viewer here is going to look like white on white. But this is the graphic we will be using, and as a matter of fact, we can do that first within the project, though I do need to begin the project So let us now start a new XNA game, and we can simply call this something like callback test. And this will be our test project. To kick things off, I'll get that graphic loaded into our content subproject just so that is out of the way and ready to go. So we could very simply pull up our ball.png file and drop that into content. We see that pulled into the project, and we are now good to go. Before I jump into the actor class, there's a few things I want to set up in-game, and that is the screen resolution, simply because I will later need this inside of actor. Since actor is bouncing off the edges of the screen, it needs to know, well, what are the dimensions of the screen. So beginning here in the game class, I'll start off by defining two public constants for screen width and screen height. First will be public const integer screen height, and we'll set that to a value of 800. Then I can simply...
I'm going to do the width, 800.
Width first? Oh, okay, I'm sorry. I've actually got that backwards. If I had left it like that, we'd have a nice narrow style screen.
Very interesting. Cool.
But yeah, once again, it's actually the width, which will be 800, and the height will be 600. This will simply match the default for an XNA game, but we now have the data defined such that we can access it from somewhere else.
Okay.
Now, just to make this whole example sane, I will use these when we're setting our graphics actual resolution. Even though we won't see a difference, it does mean that if you start to monkey around with things and change these values, you will have the actual resolution updated appropriately. So I'm going to take our graphics device manager, and we'll set the preferred back buffer width and height. So preferred back buffer width will be equal to screen width. And then to save on just a bit of typing, we could also copy and paste to duplicate that line where we will set the preferred back buffer height equal to the value held in screen height. And that takes care of just the simple setup here. What we can do now is jump into the actor class and actually write the whole actor class end to end. And once we get done with the actor class, we should be able to use it in a sense where it bounces around the screen with no additional functionality. So let's begin by adding a new item to our project. This new item will be a class that I'm going to call actor.cs for the file. And for this actor class, before we jump into the class itself, I'm actually going to add in the necessary using statements. I'm going to take out system.text because we won't be using anything held within. I'm going to add using Microsoft. Grab some spelling, and Microsoft.xna.framework, and I'm also going to be using framework.graphics. I'll be using this for things like the texture that's going to be held within the actor when it draws itself. And one other thing I will do is I'll actually declare our callback delegate from within the actor class, since it's meant to be used with actor. And as a matter of fact, you'll see in just a second, we're actually going to have it require an actor to be passed to it. So what I'll do here is I'll declare a delegate, and this will be a delegate with a void return type. The name of the delegate is simply going to be callback delegate. And callback delegate is actually going to need to take in an actor. And we'll simply call that actor sender as the name of the parameter. So now when we get down to the actual actor class, let's define the fields that we're going to use within it. Now, as we've used in past examples, I'm actually going to have the actor class contain a static list which auto-manages the list of all actors in existence. So we'll begin with a public static list of type actor. And I'll instantiate it right off the bat, and then that way I don't have to use a static constructor. So static list, and I suppose it would also be a good thing to name the list itself. Or we're going to refer to this as actors. So the field name itself will actually be actors. And we can move on to the instantiation where we say that it is a new list of type actor. Alright, moving on from here, now we need a set of fields to represent the state of any given instance of actor. And this is going to include things like position, velocity, color, texture, and the delegate itself. That will be an instance field per actor.
Which is very cool that they're getting to see this as an instance field as opposed to just a variable.
Because think about the implications of being instance is that means different actors can actually have different callbacks. So different things can happen when different actors bounce.
Exactly.
Even though it's all the same class. So to begin with some of the more simplistic fields, let's drop down position and velocity. I'm going to make all of these public just for brevity's sake, and we won't worry about accessor properties or anything like that. So we'll make a public vector2 called position. We'll make a public vector2 called velocity. And we'll make a public color field called color. And we'll set that up to be, or excuse me, to default to the color white, just so that we don't end up with a default color being completely transparent and therefore resulting in invisible actors. We'll also have a texture 2D, which I'll call texture. And finally, we have our callback. This is once again just going to be an instance field, so we'll have a public field of type callback delegate, and we'll simply call this callback. All right, now we can move into some of the methods themselves. As a matter of fact, let's begin with the constructor for actor. We'll make this a public constructor, and we'll take in a texture 2D. So we'll simply require that a texture 2D be provided at the actor's construction. And we can call this parameter texture. And the two things that we need to do inside of the constructor is, one, make sure that this instance gets added to the static list. So we'll take actors, we'll add this instance. We'll also turn around and make sure that the texture passed in is assigned to our instance field. So we'll take this dot texture and set that to the passed in parameter texture. Alright, now we have a handful of methods that we're going to need to have inside of actor. I'm going to skeleton these out, and then we'll move back in and flesh in their implementation. The reason I'm going to skeleton them is the earlier methods are actually going to need to have the latter methods in existence before they can be called. So to drop a skeleton in, we're going to need methods like a move method. So I'll make a public void move. Move is going to take in a vector2 to describe the amount of movement that should occur. And
go ahead and throw it in.
Yeah, let's get some spelling on amount. Alright, next method we'll need is going to be draw. We'll make a public void draw method, and draw will take in a sprite batch to use when drawing itself. The next method we'll have is check wall collision. This will be called every time we're moved to see if this movement has caused a collision. So this will be a public void check wall collision. And one final method we'll need will be a method called process bounce. And the reason I'm setting it up like this is because check wall collision is going to make is actually going to do 4 different checks to see if we hit the top, bottom, left, or right edge. But I want to have one generic thing happen regardless of which edge it was. So instead of putting specific code in 4 different places in the if statement, I'll actually put that off onto another method. So that way, if anything that's generic to wall bounce needs to be adjusted, we can do it from one method instead of 4 places. So I'll make this a public void method, and we'll call this method process bounce. I would actually call the method bounce, except that would imply that this method causes the actor in question to bounce, and really it has no bearing on if the actor bounces or not. It's what happens after a bounce occurs. Alright, now we've got these methods skeletoned together. Let's go back up to move and drop their implementations into place. The first thing that move is going to need to do is to take into account the amount given and then add that onto position. So we'll take this dot position and increment it by amount. And that will accomplish the actual movement. Now after every move is done, we need to see if that move resulted in a collision. And this is done in the check wall collision method. So I'll make a call to check wall collision. And there we go. Once again, that's why I needed skeletons in place here, is because we needed this method to exist. Alright, moving on to draw. Draw is very simple, and so I'm going to use the given sprite batch to perform a draw call using the instance field texture for texture. It's going to use the current position for position and the current color. I say current, but I'm meaning instance field color for color. And that takes care of our call to draw. Now we get down into check wall collision. This one's a little bit lengthier just because we have 4 separate checks that need to occur, and then different directions or different components of position and velocity, either in the x direction or y direction, need to be affected. So we'll begin the if statement, and let's begin with the left edge of the screen, where x may potentially go less than 0. So we can do a check of if this dot position is less than or equal to 0, or excuse me, this dot position dot x. That would have, I'm sure the compiler would have been really happy with us trying to compare position to an integer. But if the x value, so left side of the screen, is less than or equal to 0, then we have collided with the left-hand side of the screen. If we've collided with the left-hand side of the screen, we'll do 2 things. We'll first ensure that the position is reset back to 0. This handles the case that x was in fact less than 0. We snap ourselves back out of the wall so we never run into a scenario where we get stuck in the wall.
And we'll do that to x, of course.
Oh, yes. I guess I was a little bit happy when I was testing this code earlier, because...
I got you.
All right.
I'm just starting to think you have something against x.
I don't know, I guess another part of the code, maybe some other project I was working on, I was just using arbitrary values against vectors.
I gotcha.
Instead of setting the vectors components individually. Either way, I'm sure the compiler will be more than happy to alert us to any case that we've actually left that in.
True.
One other thing we do need to do on collision is also reverse the direction, so we start moving opposite of whichever direction was bounced. In that case, if we have hit the left edge of the screen, we would need to reverse our direction by taking our velocity's x value and inverting that. So we'll do that by multiplying against -1. And since we have just bounced off the left edge of the screen here, we'll also make a call to process bounce. That way any generic code that needs to happen on wall bounce will occur from that call. Now, if we have not collided with the left-hand side of the screen, then we still need to do a check and see if we've collided with the right-hand side of the screen. So we can put in an else if and check to see if this dot position dot x has reached or gone past the right edge of the screen, or is greater than or equal to our screen's width, which can of course be found in game1.screenWidth. Now, since we haven't, since we're looking at this texture with an origin of 0, 0, we also need to account for the fact that our circle graphic itself also has width. So we'll subtract that back off with this .texture.width. Again, this of course means that we'll check the right edge of the texture for collision instead of the left edge of the texture. And if we have collided with the right-hand side of the screen, we'll make sure we snap ourselves out of the wall. So I'll set this .position.x equal to, getting a little lazy here, I'll grab this value which represents our graphic being on the right-hand side of the screen and simply drop it in place. Then we'll also take our velocity in x and reverse it. Ah yes, reverse. That's the word I was looking for when I said that we were inverting. We're not inverting the velocity so much as we are reversing the velocity. And since this is also a bounce, we'll make a call to process bounce. Alright, that takes care of collisions, wall collisions in the x-axis. The code is essentially the same thing for the y-axis, so I'm going to copy that entire block, paste it to duplicate it, and then we'll make a bunch of changes from x over to y. So we're looking for, let's say if we're looking at the top of the screen, that would be y being less than or equal to 0. We'll snap our y back to 0, and we'll reverse our direction in y. Otherwise, if we haven't hit the top of the screen, we'll check the bottom. So we'll see if our position in y has hit the bottom edge of the screen, where bottom in this case is going to be represented by the screen dimension height. And then we'll look at our texture's height, so it measures the correct edge of the texture. And again, I'll snag screen height minus texture height, paste that in place for our snap out of wall code. Again, making sure we change our position to y. And once again, we will reverse the velocity in y, all the while calling process bounce. And now that leaves only the process bounce method. And process bounce is only going to check the callback and make a call to it if necessary. And I say if necessary because setting our callback is optional. There's nothing that says that that field has to be set to anything other than null. So we want to make sure that we check that the field is not null before we call it. Otherwise, we'll hit an exception.
And that's something that's very important that we did not talk about at the beginning of this video when we went through all of the regular lecture, And that is anytime you go to call a delegate, you should check to make sure that it's not null before you try calling
Exactly.
it.
The only exception to that is in cases like where we had on the whiteboard, things where we had literally just instantiated a new delegate right then. In those cases, it would probably be okay because you just did that on the previous line.
But here, you're far removed from where it actually got set. So did it really get set? So it's a good thing to check it.
Because in many cases, a delegate really is just a type. A type can be a field. A field does not necessarily have to be set. It could very well just be null.
Yeah. Fortunately, it's set to null when the object is instantiated, which is a nice thing. But anyways, need to check it.
So we'll do that. And the other nice thing about that is that really does mean that in code and using this code, it is truly optional whether or not you set a callback. If you have an actor for which you don't care about what happens when it collides, you can just ignore it. You don't have to process the callback. So once again, more flexibility is given by using code in this manner. But once again, now down in process balance, we will in fact do that check on this dot callback and make sure that callback is not equal to null. And if it is not null, then we will invoke it. So we'll say this dot callback, and then we're looking for who's the sender of this callback. Well, that would be ourselves. So we'll pass in this as the current instance of an actor. And that should wrap up the actor class. Before we move away from it, I would like to build very briefly and just make sure that there are no simple errors. And there are in fact no errors, only one warning as to the fact that callback has not yet been used. So now let's jump back over into game, and let's put an actor into use. As a matter of fact, let's actually set an actor up in the game and have it bounce around before we even worry about any of its callback functionality.
Okay.
So let's jump down into load content. From here, let's load our texture asset in, and let's also instantiate a new actor. So I'll make a texture2D local variable called texture. And grab some spelling, and that texture will be equal to content.load, and we're loading a type of texture2D for this asset, and we'll feed in the name ball. Now we can turn around and make a new instance of actor. So we'll say actor, I'll name the variable ball. We'll set that equal to a new instance of actor. Actor requires a texture2D, so we'll feed in the new texture variable we just created. Now with this new ball, let's set it up somewhere that makes sense on the screen, somewhere near the middle of the screen. So we'll take our ball's position and set it equal to a new vector2 of 400 by 300. And I know that won't be exact screen center because our actor is not actually centered around its origin. Right. It's actually centered around its top left. But that will be close enough. All I'm using these numbers for is to get the actor off the top left edge of the screen. And let's see, let's also give our ball an initial velocity. So we'll set our ball's velocity equal to a new vector2 of 5 by 2. So we'll move more along x, or move faster along x than we will along y. Now we also need to code in our update and draw for the game. Update needs to go through all actors and move them, and draw needs to go through all actors and draw them. So down here in update, we'll make a for loop. And I'm actually going to make a reversed for loop. I can quickly grab one by typing for, 2 R's, and then typing tab twice to bring up the code template. And the reason I'm making a reverse for loop is because I want to be able to remove actors at will and not mess up the update loop. So we can use the index variable I, and we'll loop starting at our actors count. So we'll take actor.actors.count. We'll actually take count -1 so we can grab that actual element. Now inside of the loop, we need to, well, we don't need to, but I'm going to make an actor variable just so I don't have to access the actors by actor.actors sub I every time I want to grab a field. So we'll make an actor variable equal to actor.actors sub I. Then we can turn around and move the actor by its velocity. So we can say actor.move by actor.velocity. And that should handle actor moving. Now we can jump down into the draw method, and we'll make our calls to sprite batch begin and sprite batch end. And then between those calls, we'll loop through all actors and draw them. I'll use a for each here because that way I'll automatically get an easy-to-use variable name set up, and we're not going to worry about things magically disappearing while a draw call is going on, so I'll simply loop through them in a forward manner. So for each actor, variable name actor in actor.actors to grab our list. For each actor, we will simply say that actor draw itself using our game's sprite match. And if I wanted to, I could actually take the curly braces off to compact that a little bit. Since again, this is very simple. Just draw all actors in a forward sense, the end. And with these things in place, we should actually be able to test and see an actor move around the screen. So if we build and run our game, we see this ball graphic spawns and is bouncing around all edges of the screen. And I believe that has, with that top bounce, has gotten all edges, everything working perfectly. So, now that we have a working actor, let's take a look at this actor's callback functionality. What if we now would like to specify some functionality to occur on wall collision without changing actor? Well, to do that, we could write a callback handler from within our game, or any place that we choose really, and then assign that to the actor's callback. So what I'm going to do is jump up right above the game's constructor and make just such a method. Make this be the callback handler. So make a void bounce remove method, and we'll make sure that our method signature on this method matches the delegate. So just to take a quick peek back over at actor, we can see that our delegate is defined as being a void return type and requiring an actor parameter. So to satisfy that, void return type, bounce move is the method name, and we'll take in an actor, which I'll call sender. And the functionality that I'd like to occur for bounce remove is simply to have the actor in question get removed from the scene entirely. So we can tell the actor list to remove it. So if we look into actor, grab the actors list, we can tell that to remove the sender. So this should simply cause actors to die upon collision with the wall. So now to specify that that's the callback that we would like when we instantiate the ball, we can jump down here to load content, take our ball, and tell it that its callback should be equal to a new callback delegate, where we'll hand in the bounce remove method.
And before we move on, in this particular case, you guys are seeing the ball.callback plus equals, and we had talked about on the whiteboard when declaring a delegate variable and turning right around on the very next line without it having been instantiated and saying, take this variable plus equals and then assign it a method that's going to go on the invocation list, that would give you an error. That is true. In this case, we're looking at a field, and when the instantiation occurs for actor, all these objects are set to null. Everything's set up, basically. If you were to use the straightforward example we were giving in a console app where you create a delegate variable type, and you set it to null, and then you turn around and use plus equal, that'll work just fine.
The key difference here is really the idea of a local variable versus a field.
That's right.
Where a local variable can actually be in a state of uninitialized, whereas a field is going to get hit by the field initializers for that class.
Exactly.
And is going to get initialized. If we want to take even a closer look, what I could do is I could actually set a breakpoint on texture using texture as an example of a local variable. Mm-hmm. If we run up into this point, texture, I guess in this case it's null. Well, all right, tangent didn't work. What I was going for was to show that texture can't be used if it's not if it's unassigned, meaning if we did something like this. And I see why too. This is actually just on the pre-parse phase here. We're actually going through and noticing that it's unassigned.
Right.
And that would be the error that we would try to get. If texture were a delegate and we tried to assign something to it, we couldn't even assign it normally.
Right.
Because in this case, it is simply uninitialized versus a field, which is going to begin life as null thanks to
it's initialized. It's null, but it's still initialized.
Exactly. All that goes back to the fact that I can now use plus equals.
And there's some terminology that I'd like to go ahead and throw out there that you're going to hear. I'm sure Logan's going to start saying quite a bit as we get into Space Fighter, and that is basically in this case we're subscribing to. So plus equals, you're going to hear that as used as the word subscribed often. Okay.
And another thing with plus equals is that kind of a little bit comes from a habit in using actual events,
Right.
which we'll get into here shortly. And in that case, you actually have a nice code completion template that goes along with it. So part of the reason I use it is just to actually speed code thanks to the IDE.
Right. So you can read this as we are subscribing the bounce remove method to the callback.
Exactly. So with that, and then one last thing to point out is there actually would be no problem in putting equals there.
Right.
To more closely match the example from the whiteboard. But in either case, I just did plus equals as a habit.
Mm-hmm.
But now looking back at all this, what we have done is we have now subscribed to the callback, or rather subscribed this bounce remove method to that callback, meaning that our game class can now be aware of whenever an actor hits an edge. And we get alerted by a call to bounce remove, and then we're allowed to do whatever we want with the actor passed in. And so to give it a visual result, I'm simply removing that actor altogether so we get to see it disappear.
Right.
To test this, we can run and watch the actor hit the edge of the screen and, well, disappear.
Good.
So now that we've proven the fact that we can, in fact, make a handler, one other thing I want to point out, too, is the fact that this callback does not get called until the event in question takes place. Meaning if I were to set a breakpoint and run the game, we should see a brief moment where we see the actor moving before it hits. That means many actual ticks, many actual calls to update our run before this method gets called. You can see we're running, and it's not until collision that our callback actually occurs. So that's where you can set up callbacks to hit key events instead of all of the time. Now, one last thing we could do is we could actually go through and just have a little bit of fun with the app now and make a few more callbacks to show how we can make different actors do different things. Let's move on and let's make a second callback, and let's have this callback handle changing the actor's color to some other indexed color. What I'll do to accomplish this is I'll actually make a few fields inside of our game. I'll make an array of colors and an index. That way we can have a color that changes continuously, meaning we can have an actor that upon wall collision will turn from red to green to blue to yellow, then back to red, and have that cycle continue. So I'll make a color array, which I'll call colors, and we can initialize that to a new color array, and I'll actually fill in each of the elements here as well. So we can have color.red for element 0, we can have color.green for element 1, color.yellow for element 2, and color.blue for element sub 3.
Blue or black?
Oh, and I was getting on autopilot there for a second with IntelliSense. And I'll make sure we give a terminator here to fill off the end of our field. And I'm also going to make another field. This is going to be an integer that simply holds what color we're currently on. I'll call this field color index. And we can set that to 0 just to explicitly define where it starts at. Now that we have these fields in place, we can now maintain state between callback calls. So what we can do now is if we write our callback as void bounce change color, and again we will take in an actor named sender. What bounce change color is going to do is it's going to take that sender actor, it's going to set its color to be equal to the current color. So that would be colors sub color index. So if we look at what will happen the first time, color index is going to start at 0, so we set it to colors sub 0, which is going to be the color red. So the first bounce to change our actor from its initial white color to a red color. I'm also going to take color index and do a post increment on that, and that way that's just shorthand for not having to increment the color index on a separate line. Mm-hmm. So that way we'll grab element 0. Once that line is done, we'll post increment it so that for the next call it will then be 1. And then one other thing I'll do is I'll actually take color index and I'll modulus equals it against the color's length value. And this is simply to ensure that color index will repeat back at 0 if it goes over the number of existing colors, which means valid colors would be like color sub 0, 1, 2, 3. The moment we hit a color index of 4, I would like that to wrap back around to 0. So 4 modulus equals 4 should store a value of 0 back in color index. So with this in place, let's make another actor, add another actor to our scene, but have its callback be set to bounce change color. So what I can do is I can copy our code that is down in load content for creating the new actor, though since this variable has already been declared, I'll take out the declaration of actor there. So we'll just reuse the same variable to point to a new actor since it's thrown away at the end of this method anyway. So we'll say that ball is once again equal to a new actor. We'll take this actor and we'll move it a little bit just so that the actors aren't on top of each other. I'll move this to a position of 200 by 100. We'll leave the velocity the same so that they're easy to track on screen. And this second ball's callback is going to be bounce change color. So we'll have our first actor, it's closer to the wall, so we should see it get removed. Then we should see the second one further to the left, and it will simply change color upon bounce.
So the key thing to remember here is you're going to see two objects that were forged from the same mold, from the same template, but each having different functionality. But the cool thing is, as far as the template for these objects, the balls, are concerned, it had no clue about this functionality.
Exactly. So if we run, first ball gets destroyed, and the second one continues to bounce, but now it has additional functionality in that it changes color upon bounce.
And this is very cool.
And again, going back to what you were saying just a second ago, what's cool about this is the fact that it's almost as though we are extending the functionality of actor, but we are doing so making no changes to the actor class itself.
Exactly.
And while we're in here having fun, there's no reason we can't add one more callback. This one, honestly, just for more fun. What I'd like to do now is make a callback that causes additional circles to get spawned every time a circle bounces off the edge of the screen.
Nice.
So to do that, with this new circle that gets spawned upon bounce, I would like the new circle to get shot off in a random direction instead of the current one or the reverse of the current. That makes a nicer, more scattered look on the screen. But in order to do that, I'm going to need a random object and a utility method in order to cleanly obtain a new vector direction. So what I'll do is for the field, that will be easy enough. That will simply be a new field of type random, which I will call random. And I will instantiate using a field initializer. And I'm also going to need a utility method, so I'll drop that in wherever seems convenient, I guess right above the game constructor. And this utility method is going to be called calc random direction. His job is just to simply come up with really a random rotator, or excuse me, a random, what's the word, opposite of degrees? Radians, yes. Its job is to come up with a random number that is in radians, and then use that value in radians to generate a new vector2 pointing in any possible direction around a circle. A lot of words to describe what it's going to take 2 lines of code. So let's begin with our method. It will return a vector2, and it will be called calc random direction. Calc random direction is first going to come up with that initial rotational value, that initial angle in radians. So I will make a float value called angle, and this float value will be equal to random.next. Since there isn't a next float, I'm going to use next double, and I'm going to cast that to a float. Now this is going to give a value in the range 0 to 1. That is not a full circle in radians. What we need to get a full circle is pi times 2. And we can access that in a convenient constant held in math helper dot 2 pi. And that's the value that will actually give us a full circle. Now to change this value in radians over to a directional vector, we can use sine and cosine for the x and y components of the vector. And since this is the point, and since a vector2 is what we want out of this method, I'm not even going to bother storing it. I'm simply going to return the new vector2, where x is the function of, the sine of the angle, and y is the cosine of the angle. So we'll have math.sine of angle. And sine is, of course, a double. Vector is going to require a float, so we'll cast that over to float. And then we'll do pretty much the exact same thing for y. A cast to float result of math.cosine, and the cosine is of the given angle. So finish off the parenthesis for vector2, terminate, and that should take care of calc random direction. Now we have everything we need for a more interesting callback. let's now make our callback method a void called bounce spawn. And let's see, just looking at spelling for a second. This is going to take in, of course, an actor. I'll name that actor sender. And bounce spawn is going to cause a new actor to get created. And it's not actually going to modify sender whatsoever. So for the moment, sender is actually completely redundant here. We have to have it because our method signature has to match, but we're not forced to use it, so we're just going to disregard it. What I am going to do is make a new actor variable. And the name of this variable can be something like new ball. A new ball will be a new instance of actor. And actually, I'm going to take back what I said a second ago. We actually do need sender. Since the instantiation of actor requires a texture, and we did not maintain our texture 2D as a field, we actually just got lazy and made it a local variable. That means we don't have any access back to that texture. But if we're looking at an actor, we know that that actor has a texture, and we can just steal it. So we're going to keep things simple and just make things up as we go, as it were. We're actually just going to take our sender's texture, and it all works out in the end because we only have one texture, so we'll just grab the most convenient instance of texture. Alright, but once we do in fact have a new ball, we'll set up its position and velocity based on, well actually we'll set up the position based on the current sender. So that's, new ball dot position equals, so really we're using sender all over the place.
Yeah.
So take what I said a second ago about disregarding sender and do the exact opposite of that. We're going to use our sender's position. So again, we'll spawn a ball at the point at which this ball hit the edge of the screen.
Mm-hmm.
I want to take our new ball's velocity, and we'll set that equal to, now since, in this case, the way I'm using velocity is I'm kind of combining direction and speed into one vector too. So velocity actually needs to be that new random direction, and then we'll multiply that by our current sender's velocity. We'll actually extract a length from its velocity. So that way what's interesting is we're kind of taking the vector 2 apart, grabbing just its speed, and then multiplying that by our new direction to get a final velocity. So we're actually taking velocity, separating it into speed and direction, then putting it all back into velocity. So to type all that out, that's velocity equals calc random direction, which I guess to give a more concise term, that means we're going to get a unit vector back out of calc random direction. And we can then multiply that unit vector against some arbitrary number to give an overall length. So we can get sender dot length. And the reason I'm getting sender dot length is I want this new object to go in a random direction, but with the same speed as the actor it was, I want to say spawned from, but spawned near.
Mm-hmm.
So that is sender
Velocities.
Velocity dot length. So it's almost like we're copying the speed, but applying a new direction. And so with all of that, we should now be able to take our ball and change its callback to bounce spawn. And now whenever the second actor hits, a new actor gets created. And it very quickly becomes confusing as to which one is the one that has the callback assigned, as all of the circles are the same color. So I'm going to take the ball, the first ball, and change its color to color.gold. That will give a nice orangish color that contrasts with the background. So you can see that the orange circle is now the one that has the callback assigned, and all the ones that get spawned later have no callback assigned, once again showing the fact that the callback is optional. Because at the moment our code doesn't care about all of these new circles, it only cares about the first one. But if we wanted to, we could actually create a really interesting cascade effect, because what would happen if every new spawned circle also had a callback that spawned more circles? Well, before I go that far, I'm actually going to take our callback on bounce ball, just to show the callback on all the new objects, where did that callback go? Bounce spawn. To show a more simple and less catastrophic example, we could take new ball, and we could assign a callback, callback equals, let's say, new callback delegate, bounce, let's do change color first. So now we should make each of the new instances of actor have some callback functionality. They change in color. So The gold or the orange circle does not change color. Instead, it spawns more circles. The new circles each change color upon bounce.
Very nice.
Now we have a more dynamic scenario where actors can get spawned, and then those new actors also have callbacks that we're interested to, also stemming from the game. Now, one other thing we can do here is let's actually test a multicast delegate. What if we took each of our new circles and assigned 2 methods into the invocation list? So what if we took the second one and actually did a bounce spawn? So each of these newly spawned circles not only changing color when they hit walls, they also spawn more circles, which will in turn bounce around the screen. So actually, each of those new bounce spawns are going to actually be here, so they'll change in color. So those, in turn, will get a callback that is a multicast delegate, which also changes color and spawns.
That's right.
More circles. Of course, I don't have any cap set on the number of circles, so this will simply degrade until our game gets slow and then locks. So if we watch, first bounce, get an extra one. That one bounces and spawn 2. And each of those, everything that spawns more. And then we get into a nice runaway scenario. So here in a second, things will chop up, and I'll just close the game because I don't feel like having to break out of the sequence to kill it.
Right.
But again, that shows the flexibility that we're given. We're not only allowed to now extend functionality, but we can also start to stack functionality onto everything that we create.
Very nice.
So very, very interesting effect there. So with that, I think that really wraps up the example that I wanted to show. Again, this example just showing how we can use delegates to our advantage inside of an XNA game, where we can extend the functionality of an actor without having to modify the actor. That extended functionality can actually be provided as callbacks inside of our main game class.
Okay, and from here we're going to move into some more videos looking a little closer at delegates. Taking everything that we've learned and apply it to some more practical examples. And with that, that is going to conclude this video. Thanks a lot, guys.